June 27, 1951. Lima, Ohio. The engineering report from visiting European hydraulic specialists would never fully capture what they witnessed that morning in the Lima Locomotive Works assembly hall. American factory workers building excavation equipment using mechanical principles that defied everything European precision engineering said was necessary for modern construction machinery. Through the steam and hammering of the Ohio factory floor, massive steel shovels took shape with components sized far beyond what mathematical calculations required. No delicate hydraulic systems, no computer controls, no precision machine parts requiring specialized maintenance. Yet they would outlast every sophisticated excavator European manufacturers could design. In European factories, hydraulic excavators promised revolutionary efficiency through complex systems operating at 5,000 pounds per square inch. Precision engineering, computerized controls. Maintenance schedules measured in thousands, not tens of thousands of operating hours. Most carried performance guarantees no longer than 15 to 20 years maximum service life. The Americans were operating with mechanical philosophy the Europeans had dismissed as outdated brute force. Oversized cables, direct mechanical advantage, steel components built to handle 3 times calculated stress loads, reliability measured in decades, not years. 800 miles from European research laboratories, the most decisive excavation equipment revolution in construction history was revealing itself. Not in hydraulic sophistication, not in computerized precision, but in mechanical dominance that would keep 1950s shovels digging 4 cubic yard buckets, while 21st century excavators failed after 15,000 hours. The telegram from New York Central Railroad arrived at Lima Locomotive Works on a Tuesday morning in spring 1922 that would change American heavy industry forever. Telegraph operator Herman Muller tore the yellow Western Union message from his machine and read the words that made his hands shake slightly. The railroad's message was blunt and desperate. European-trained engineers declared 2,500-ton freight trains over Berkshire hills impossible. Need locomotive with 30% more power. Can you deliver what theory says cannot work? William E. Woodard stood in the company's sprawling 100-acre works, studying the challenge while the industrial symphony of Lima's production echoed around him. At 34, Woodard had already earned respect as Lima's most innovative mechanical engineer, but this telegram represented something far beyond routine locomotive design. 2,400 workers hammered, riveted, and assembled the Shay-geared locomotives that had built Lima's reputation since 1878, their labor creating the rhythmic industrial music that had powered Ohio, manufacturing for decades. But this request was different. This was about proving American mechanical engineering could exceed what European technical schools taught was physically possible. The established wisdom came from the most prestigious engineering minds in the world. European locomotive designers educated at technical institutes in Germany, Britain, and France had spent decades calculating the precise limits of steam locomotive performance. Their mathematics was elegant, their credentials impeccable, and their verdict final. No locomotive could maintain adequate power while climbing the 1.5% grades of Massachusetts's Berkshire hills with 2,500 tons of freight cars trailing behind. The physics were clear, the calculations verified by multiple engineering authorities, and the conclusion unanimous across the Atlantic engineering community. But Woodard had developed a fundamentally different philosophy during his 15 years of practical American problem solving. He called it superpower, and it represented a complete rejection of European theoretical limitations in favor of mechanical dominance through brute force engineering. While European designers focused on mathematical efficiency and theoretical optimization, Woodard focused on mechanical reality amplified by massive structural strength. His approach was deceptively simple. Build every component to handle forces 300% beyond calculated requirements, and the machine will exceed theoretical performance limitations. The engineering challenge before Lima was unprecedented in its scope and stakes. The target specifications seemed impossible. Move 2,500 tons up a continuous 1.5% grade at sustained speed. European calculations had established the maximum possible tonnage at 1,800 tons, beyond which any locomotive would stall on such grades. The required innovation demanded a 30% increase in sustained power output, which violated fundamental thermodynamic principles as understood by established engineering theory. Woodard's radical approach abandoned conventional efficiency calculations entirely. Instead of optimizing fuel consumption or mechanical precision, he designed systems that captured and amplified power through direct mechanical linkages, built to dimensions that seemed wasteful by European standards. His superpower principles specified fireboxes 40% larger than mathematical models suggested necessary, steel components designed to handle 3 times calculated stress loads, and direct mechanical advantage systems that routed power through simple, maintainable components rather than complex precision mechanisms. The stakes crystallized as autumn 1922 arrived with devastating clarity. Lima Locomotive Works had barely survived the crippling recession of 1920 that had bankrupted dozens of American manufacturers. Orders remained scarce. Competition from established companies like Baldwin Locomotive Works grew fiercer daily, and the entire engineering establishment had united in skepticism about Lima's unconventional approach. The prototype locomotive would cost $85,000, equivalent to over $1 million in modern currency, and require 8 months of continuous development work by Lima's most skilled craftsmen. If Woodard was wrong, if European engineering theory proved correct about fundamental physical limitations, Lima Locomotive Works would join the growing list of failed American manufacturing companies that had gambled their survival on innovation and lost. The company's financial position left no room for expensive mistakes. Creditors were demanding regular progress reports. Skilled workers were considering job offers from more stable competitors, and railroad purchasing agents across the country were watching Lima's experiment with mixture of curiosity and professional skepticism. The final devastating blow arrived in December 1922, when Pennsylvania Railroad, America's largest and most influential transportation company, announced their decision to purchase 45 new locomotives from Baldwin Locomotive Works, using what they specifically described as proven European engineering principles. The public rejection by such a major customer sent shockwaves through Lima's management and workforce, confirming the industry's commitment to established methods over unproven American innovations. As 1922 ended in bitter Ohio winter, Lima faced the stark reality that they were betting their company's entire future on mechanical engineering philosophy that contradicted everything the experts taught. Snow covered the sprawling works where 2,400 families depended on Lima's success, while inside the heated assembly halls, skilled craftsmen began building what critics throughout the industry had already labeled Woodard's folly. The machine taking shape on Lima's assembly floor would either revolutionize American heavy industry by proving that mechanical dominance could overcome theoretical limitations, or destroy the company that dared challenge European engineering authority with nothing but American determination and oversized steel components. The sound echoing through Lima's erecting halls by January 1923 was unlike anything heard before in American locomotive construction, the ring of hammers shaping steel plates 30% thicker than any blueprint had ever specified. Woodard's prototype locomotive, designated A1, was taking shape as a monument to mechanical overkill that challenged every convention of railroad engineering. Master machinist Otto Brennan ran his calloused hands across the massive firebox walls, feeling steel thickness that seemed excessive even by Lima's generous standards. At 100 square feet, nearly double the size of standard locomotive fireboxes, this combustion chamber required support structures that dwarfed conventional locomotive frames. "Mr. Woodard," Brennan said, his German accent still thick after 20 years in Ohio, "this firebox could heat a small factory. You sure she won't shake herself apart under all that pressure?" The veteran machinist had built locomotives for 15 years, but nothing approaching the A1's massive proportions. Woodard smiled at the reaction he expected from men trained in European precision engineering. "Otto, we're not building a watch. We're building a machine that will outlast every locomotive our competitors can design." The firebox walls measured 1¼ inches thick, nearly 50% heavier than standard specifications, designed to contain working pressures of 250 pounds per square inch sustained operation. The revolutionary engineering philosophy manifested in every component taking shape across Lima's assembly floor. Where European locomotives relied on mathematical precision to optimize efficiency, the A1 embodied Woodard's belief that mechanical dominance trumped theoretical elegance. The firebox generated 4,400 British thermal units per hour, 40% above what established thermodynamic calculations declared theoretically maximum for sustained operation. Heat output that European engineers insisted would destroy any locomotive boiler through thermal stress became the foundation of Lima's power advantage. The A1's valve gear represented Woodard's core philosophy, translated into working mechanical systems. Instead of complex European-style precision mechanisms requiring specialized maintenance and factory-trained technicians, he designed massive overbuilt components that any railroad shop mechanic could service with standard tools. The main driving rods weighed 640 pounds each, twice the standard weight that European efficiency calculations recommended. Critics throughout the industry called such specifications wasteful and economically unsound. Woodard called it mechanical insurance that would prove its value when forces exceeded design limits. When stresses reached critical levels, these oversized components would flex rather than fracture catastrophically. When repairs became necessary, any railroad maintenance facility in America possessed the equipment and expertise to handle them. European locomotives required specialized parts manufactured to precise tolerances by the original builder. Lima locomotives could be repaired by blacksmiths with hammers and welding equipment available in every railroad town across the continent. The first test runs on Lima's private track in June 1923 revealed both the unprecedented promise and the unexpected problems of Woodard's approach. The A1 generated power levels that exceeded every measurement Lima's engineers had recorded from conventional locomotives. Test cars loaded with 200 tons of scrap iron climbed grades that stopped standard locomotives completely, while the A1's massive firebox maintained steam pressure that never wavered. But the enormous forces created engineering challenges that no previous locomotive had encountered. The prototype's first crisis arrived at 47 miles per hour during a test run toward Cleveland. A lateral rod bearing stressed beyond any previous locomotive experience began overheating as friction generated temperatures that threatened catastrophic failure. European-trained engineers observing the test saw this as definitive proof their calculations were correct. The mechanical forces involved were simply too great for sustained operation. The laws of physics couldn't be violated through brute force engineering, regardless of American optimism. Woodard interpreted the same evidence completely differently. Rather than accepting theoretical limitations, he saw a design problem requiring mechanical solutions. He ordered bearings 50% larger than his original specifications, with oil reservoirs capable of handling the increased thermal and mechanical loads. The modifications cost $1,200 and delayed testing 3 weeks while Lima's machinists manufactured components that had never been built before. But when the A1 returned to service with its enlarged bearing systems, it operated continuously for 18 hours at speeds no locomotive had ever sustained under heavy load. The bearing modification revealed the fundamental difference between European precision engineering and American mechanical philosophy. European engineers would have reduced loads to match existing component capabilities, accepting performance limitations as immutable physical laws. American engineers increased component capabilities to handle whatever loads the application demanded, treating mechanical limitations as problems to be solved rather than barriers to be accepted. By autumn 1923, the A1 was consistently pulling test loads that approached the 2,500-ton target specified by New York Central Railroad. Steam pressure remained constant at 245 pounds per square inch throughout extended runs that would have exhausted conventional locomotives. Fuel consumption averaged 2.8 tons of coal per 100 miles of operation, 30% more efficient than European calculations had predicted for comparable power output. Word of Lima's achievements began spreading through railroad circles, carried by purchasing agents and mechanical engineers who had witnessed test runs that contradicted everything their technical education suggested was possible. The A1 wasn't just exceeding theoretical performance limits, it was doing so with mechanical reliability that surpassed conventional locomotives operating at much lower power levels. European engineering theory faced a challenge from American mechanical philosophy that couldn't be dismissed through mathematical calculations or academic credentials. The moment that would vindicate American mechanical engineering against European theoretical limitations came at 6:47 in the morning on a fog-shrouded September day in 1924, deep in the Berkshire Hills of Massachusetts. Lima's A1 prototype, now designated as the company's primary demonstrator locomotive, stood at the base of the grade that European engineers had declared insurmountable for 2,500-ton freight trains. Behind the massive locomotive stretched a consist of freight cars, loaded with precisely 25-45 tons of manufactured goods, coal, and raw materials, 645 tons beyond what European calculations declared physically possible to haul up sustained grades. Railroad officials from 5 major companies crowded into the locomotive cab, their presence representing millions of dollars in potential orders hanging in the balance of the next hour's performance. Pennsylvania Railroad's chief mechanical officer stood shoulder to shoulder with purchasing agents from New York Central, Baltimore and Ohio, Chesapeake and Ohio, and Norfolk and Western, men whose decisions would determine whether Lima's radical engineering philosophy gained industry acceptance or remained an expensive experiment. Engineer Bill Matthews, Lima's most experienced test operator, placed his weathered hand on the throttle lever while studying the steam gauge that showed 245 pounds per square inch of working pressure. "Gentlemen," Matthews announced to the watching officials, "we're about to find out whether Mr. Woodard's mathematics work better than European textbooks." The locomotive began its assault on the 1.5% grade that climbed continuously for 8.2 miles through the Massachusetts mountains. European engineering calculations had established this route as the definitive test of locomotive capability, steep enough and long enough to reveal the absolute limits of steam power under maximum load conditions. As the A1 engaged the grade, its massive firebox consumed coal at rates that would have been considered wasteful by European efficiency standards, yet generated sustained power that exceeded every prediction. Steam pressure held steady at 245 pounds per square inch throughout the climb, while the locomotive maintained consistent speed that defied gravitational forces acting on the enormous trailing load. The watching officials recorded measurements that contradicted fundamental assumptions about locomotive performance limitations. 23 minutes into the climb, at the steepest section where European-designed locomotives typically stalled under much lighter loads, the A1 was still accelerating. Speed readings showed 23 miles per hour, a velocity that European calculations declared impossible for any locomotive pulling such tonnage up such grades. The mechanical advantage systems that Woodard had designed were translating thermal energy into tractive force with efficiency that surpassed theoretical maximums established by the most prestigious engineering institutes in the world. As the locomotive crested the summit and began its controlled descent toward Springfield, the watching railroad officials realized they had witnessed something unprecedented in the history of steam locomotion. American mechanical engineering had produced measurable results that directly contradicted established European engineering theory. The numbers were indisputable, the performance undeniable, and the implications revolutionary for every railroad operation in North America. Pennsylvania Railroad's chief mechanical officer, who had arrived in Massachusetts as a skeptic committed to proven European methods, immediately telegraphed his Philadelphia headquarters with a message that would reshape American locomotive purchasing. Lima Locomotive exceeded all performance predictions. European calculations appear fundamentally flawed. Recommend immediate evaluation of American mechanical principles for entire fleet modernization program. Word of the Berkshire Hills triumph spread across the railroad industry with the speed of telegraph communication, reaching engineering departments and executive offices from coast to coast within 48 hours. By October 1924, locomotive purchasing agents from railroads across North America were requesting demonstration runs for their specific operating conditions. The A1 spent the following 6 months touring the continent, pulling record loads over grades that had challenged railroad operations since the first rails were laid. Each demonstration produced results that further validated Woodard's engineering philosophy while undermining European theoretical foundations. The locomotive consistently pulled loads 30 to 40% heavier than European calculations declared possible, maintained steam pressure under conditions that should have caused boiler failure, and operated with mechanical reliability that surpassed conventional locomotives working at much lower stress levels. American mechanical dominance through oversized components was proving superior to European mathematical precision through optimized efficiency. The real validation came from an unexpected source that arrived in Lima during March 1925. A technical delegation from Germany's Krupp Works, Europe's most prestigious heavy engineering manufacturer, had crossed the Atlantic specifically to understand how American brute force engineering had achieved performance levels that their sophisticated mathematical analysis declared physically impossible. The German engineers spent 2 weeks examining Lima's design philosophy, manufacturing methods, and operational results with the methodical thoroughness that characterized European technical investigation. Their confidential report, later leaked to American trade publications, acknowledged that Lima's mechanical engineering approach had achieved sustained locomotive performance that exceeds our theoretical calculations by margins we cannot explain through conventional thermodynamic analysis. The admission from Europe's leading locomotive designers represented more than technical curiosity. It constituted formal acknowledgement that American engineering methods had surpassed European theoretical limitations through practical application of mechanical principles. The answer to German questions lay not in mathematical sophistication or theoretical innovation, but in Woodard's fundamental philosophy that prioritized mechanical reality over computational elegance. Where European engineers optimized designs to match theoretical efficiency calculations, American engineers built components massive enough to handle forces far beyond mathematical predictions. Where European locomotives failed when operational demands exceeded design parameters, American locomotives continued operating because every component was engineered to handle stress levels 3 times greater than calculated requirements. By late 1925, Lima Locomotive Works faced a transformation that validated everything Woodard had risked the company's survival to prove. Orders poured in from railroads that had previously relied exclusively on European engineering principles, while technical journals published articles analyzing the Lima method of mechanical engineering that was revolutionizing American heavy industry through the simple application of overwhelming structural strength. Success in locomotive manufacturing created opportunities that would extend Woodard's engineering philosophy far beyond railroad applications. With locomotive orders flooding Lima's production capacity through 1925 and 1926, company management faced a strategic decision that would determine the scope of their mechanical engineering revolution. The proven success of superpower principles in steam locomotion suggested broader applications in heavy machinery markets that suffered from the same reliability problems European precision engineering had failed to solve. The opportunity arrived through economic necessity when Ohio Power Shovel Company, a local manufacturer of excavation equipment, faced bankruptcy in 1928. Lima's board of directors acquired the failing company's assets not for their existing product line, but for access to construction equipment markets where mechanical reliability problems created the same challenges Lima had solved in locomotive design. Steam shovels and excavation equipment of the era suffered from notoriously unreliable mechanical systems that failed under the massive forces required for heavy construction work. European-designed hydraulic systems, while offering greater precision and operator control, required complex maintenance procedures that shut down construction operations for days when repairs became necessary. Specialized hydraulic components manufactured to tight tolerances could only be serviced by factory-trained technicians using precision tools, creating dependency relationships that increased operating costs while reducing equipment availability. Construction contractors across America struggled with excavation equipment that promised efficiency but delivered frustration through frequent mechanical failures. Woodard recognized an opportunity to apply his proven mechanical engineering philosophy to construction equipment challenges. Instead of pursuing the industry trend toward delicate hydraulic systems or undersized mechanical components, optimized for theoretical efficiency, he designed cable and winch systems built according to the same superpower principles that had revolutionized locomotive performance. The fundamental approach remained unchanged. Build every component to handle forces far beyond calculated requirements, and the machine will exceed theoretical performance limitations. Lima's construction equipment philosophy emerged through 1928 and 1929 as a direct application of locomotive engineering principles to excavation machinery. Cable systems utilized 1.5-inch diameter steel cables with braking strengths of 240,000 pounds, 3 times the maximum theoretical load any excavation operation would generate. Drum construction featured cast steel housings with 6-inch wall thickness that could withstand mechanical stresses that would destroy conventional equipment. Drive systems employed direct mechanical linkages, serviceable with basic tools rather than complex gear trains requiring specialized maintenance. Where competitors pursued gear ratios optimized for efficiency and speed, Lima designed mechanical advantage systems optimized for reliability and simplicity. Their excavation equipment moved more slowly than hydraulic alternatives, but operated continuously without the mechanical failures that plagued more sophisticated designs. Maintenance consisted primarily of cable replacement and lubrication, tasks that any competent mechanic could perform using standard shop equipment available at construction sites across America. The design philosophy proved remarkably prescient as America entered the economic catastrophe of the Great Depression. Beginning in 1929 and extending through the middle 1930s, construction budgets disappeared while contractors struggled to maintain operations with existing equipment. Lima shovels, built with massive mechanical redundancy and simple maintenance requirements, continued working when more sophisticated European-designed machines sat idle due to repair costs and part shortages that cash-strapped contractors couldn't afford. Economic collapse became the ultimate engineering test that validated Woodard's mechanical philosophy under conditions no designer had anticipated. Construction projects that continued during the Depression's worst years demanded maximum equipment reliability from machines that received minimal maintenance due to budget constraints. Lima's excavation equipment, designed with components oversized far beyond normal requirements, absorbed the neglect and abuse that destroyed more delicate alternatives. A comprehensive reliability study conducted by Construction Engineering magazine in 1934 documented the performance gap between Lima's mechanical engineering approach and European precision designs during the economic crisis. Lima shovels maintained 94% operational availability during the Depression's worst years, while European-designed excavation equipment averaged 67% availability due to maintenance issues and part shortages that idled machines for extended periods. The comparison revealed the hidden costs of sophisticated engineering during economic stress. European hydraulic excavators promised superior performance under optimal operating conditions, but required continuous access to specialized parts, factory-trained maintenance personnel, and precision repair facilities that became unavailable during economic crisis. Lima's mechanical shovels sacrificed some operational efficiency in exchange for self-sufficiency that kept them working when support systems collapsed. But as America recovered during the late 1930s, Lima's mechanical engineering philosophy faced new challenges from an industry increasingly attracted to technological complexity. American manufacturing was embracing precision engineering, specialized components, and the promise of technological sophistication that promised to make brute force mechanical engineering obsolete. Hydraulic systems offered undeniable advantages in operator control, compact design, and precise positioning that made construction work faster and more accurate. Young engineers graduating from technical schools arrived in industry with training that emphasized mathematical optimization, precision manufacturing, and component specialization rather than the mechanical dominance principles that had built Lima's reputation. The engineering establishment was moving toward complexity and precision, viewing Lima's oversized components and simple mechanical systems as outdated approaches from an earlier industrial era. By 1940, Lima faced the same credibility challenge that had confronted Woodard in 1922, but reversed. Instead of proving that American mechanical engineering could exceed European theoretical limitations, Lima now had to demonstrate that simple, robust engineering principles remained superior to advancing technological sophistication. The construction equipment industry was embracing hydraulic technology, computer-controlled systems, and precision engineering that promised to make mechanical advantage systems obsolete through superior efficiency and operational capability. The stage was set for a decades-long test of engineering philosophy that would determine whether Woodard's mechanical dominance principles could survive the advance of technological complexity, or whether Lima's construction equipment division would become another casualty of industrial progress toward precision and sophistication. By 1950, Lima's construction equipment division was producing excavation machinery that represented the culmination of Woodard's mechanical philosophy, refined through 30 years of continuous development. The Lima Model 2400 shovel, introduced in 1948 during the final years before the company shifted strategic focus, embodied everything Woodard had learned about mechanical dominance through decades of challenging European precision engineering. These machines incorporated specifications that seemed excessive by contemporary standards, but reflected Lima's unwavering commitment to structural strength over theoretical optimization. The Model 2400's technical specifications demonstrated mechanical engineering principles that prioritized longevity over efficiency. The excavation bucket held 4.2 cubic yards of material while generating digging forces of 485,000 pounds through cable-multiplied mechanical advantage systems. Crowd force reached 320,000 pounds through direct mechanical drive systems that required no hydraulic components or computerized controls. Operating weight of 180 tons reflected structural steel designed to handle 3 times calculated stress loads, while the diesel-electric power plant utilized simple, maintainable systems that any qualified mechanic could service. Expected service life exceeded 25 years with routine maintenance, a specification that seemed conservative given Lima's experience with earlier models. But these machines entered commercial service just as the construction industry began embracing hydraulic technology that promised to revolutionize excavation equipment through precision control, compact design, and sophisticated automation. European manufacturers promoted hydraulic excavators as the future of construction equipment, offering capabilities that made mechanical shovels appear obsolete. The hydraulic revolution of the 1960s and 70s offered undeniable operational advantages that attracted contractors seeking efficiency and precision. Hydraulic excavators provided precise bucket control that allowed operators to work in confined spaces around existing structures and with accuracy that mechanical cable systems couldn't match. Compact design enabled transportation to job sites that couldn't accommodate the massive dimensions of traditional mechanical shovels. Operator comfort improved dramatically through enclosed cabs with ergonomic controls that reduced fatigue during extended operation. By 1975, mechanical excavation equipment seemed like industrial dinosaurs from an earlier era. European and Japanese manufacturers had perfected hydraulic systems that delivered superior performance in virtually every operational category except raw mechanical strength. American contractors, impressed by the technological sophistication and operational efficiency of hydraulic equipment, began transitioning away from what industry publications described as outdated mechanical technology. Lima's construction equipment division closed in 1980, unable to compete against hydraulic alternatives that dominated market preferences. But in quarries, mining operations, and heavy excavation sites where maximum productivity mattered more than operator convenience or precision control, something remarkable was happening. The old Lima mechanical shovels continued working with reliability that hydraulic equipment couldn't match. While sophisticated hydraulic excavators impressed contractors with their capabilities, they also demonstrated vulnerability to mechanical stresses that Lima's overbuilt systems absorbed without difficulty. The engineering reality became apparent through operational data that contradicted the construction industry's technological optimism. Modern hydraulic excavators required major rebuilds every 12,000 to 18,000 operating hours, as precision components wore beyond serviceable limits under heavy-duty applications. Major hydraulic system failures occurred in 23% of machines annually after accumulating 10,000 operating hours, with hydraulic pump replacement costs ranging from $180,000 to $350,000 per incident. Electronic control systems, promoted as advantages in precision and efficiency, proved to be additional sources of mechanical vulnerability. Electronic system failure rates reached 31% annually after 8,000 operating hours as computerized components succumbed to vibration, moisture, and electromagnetic interference that mechanical controls ignored completely. Expected service life for hydraulic excavators topped out at 15 to 20 years maximum, assuming regular maintenance and component replacement that could exceed the original purchase price. Lima mechanical shovels demonstrated performance characteristics that violated every assumption about obsolete technology. Operating hours before major mechanical rebuilds consistently reached 35,000 to 50,000 hours, as oversized components wore gradually rather than failing catastrophically. Major system failure rates averaged 3% annually, primarily involving cable replacement that could be performed by construction crews using standard equipment. Annual maintenance costs ranged from $45,000 to $65,000, while electronic systems remained non-existent due to purely mechanical control systems. The most dramatic validation came from machines that had operated for decades beyond their intended service life. Lima Model 2400, serial number 847, built in 1951, accumulated 127,000 operating hours by 2024, equivalent to 63 years of continuous operation. 3 major rebuilds had occurred at intervals of approximately 40,000 hours, consisting primarily of engine overhauls that any competent mechanic could perform. Original mechanical components, including the main frame, boom structure, crowd mechanism, and cable drum systems, remained in service with specifications identical to 1951 factory conditions. Current production rates for 73-year-old Lima equipment matched original factory specifications of 4.2 cubic yards per operating cycle. Downtime for repairs averaged 2.3% annually compared to 18.7% for comparable modern hydraulic excavators. The mechanical engineering philosophy that industry experts had dismissed as obsolete was delivering reliability performance that modern technology couldn't approach. The vindication reached its climax in 2024 when Komatsu Corporation, the world's largest excavator manufacturer, quietly initiated internal studies of Lima shovel design, principles for next-generation mining equipment development. Confidential engineering documents obtained through industry sources revealed Komatsu's conclusion that American mechanical engineering philosophy circa 1920 through 1950 achieved reliability metrics we have never matched with hydraulic technology. In an era of computer-controlled precision, hydraulic sophistication, and electronic automation, the most reliable excavation equipment operating in American construction and mining remained those built using William Woodard's superpower philosophy from the industrial age. The machines still digging 4 cubic yard buckets after 7 decades of service proved that mechanical dominance through structural overkill remained superior to every technological advancement the precision engineering establishment had developed.